Hello, students. So we start our lecture. And it is not only introduction, but we start to do this. Chat, yeah, nothing. We start to do this. And instructions, how it will go, course and so on, I will tell later. And now we just start, and I show you, as I told, the book which we shall use. This is Complex Analysis with applications in science and engineering, Horald Kohan. And you can find it in our library at the Linnaeus University. For example, I downloaded it from the library. And more or less, we follow this book. In some way, it's not real mathematical course of complex analysis. It's more adjusted for engineers. But in any event, the main notions, and our aim is to complete few chapters, chapter 2, chapter 3, until chapter 6. Unfortunately, chapter 6, multivariate complex functions, it's the most interesting topic of complex analysis. And maybe if you will have time, I want to come back to this, but course has the second part, which is really also very heavy. This is Fourier analysis. So after we complete 5 chapters, I plan to start Fourier analysis, and if I will have time, I will go back to multi-valued functions and so on. Now you will get, maybe starting from the second lecture, you will get some problems for your training at home. And you can already download from materials. There is materials section on my model. You can download the file of the book, and there are problems, many hundreds of problems with solutions. So your strategy should be the following: try to solve without looking to solution. If you are not able, look, solution is very detailed. You don't need instructions, and see how to solve. After this, there will be a kind of pre-exam in complex analysis. And those who succeed with this pre-exam, they would not get corresponding problems on exam, on complex analysis. Okay, so we start with complex numbers. And as I know, you have them in gymnasium. And we repeat them very briefly. So I follow the book. So those who are very good book readers, you can just read the book. No, I will have some comments, which are of course useful. So the idea was the following. Since long time, people wanted to solve, to take square root from a negative real number, for example, from -1. And since few years, hundreds, maybe years of thinking, people understood that they cannot define square root of -1 as real number, and they introduced special number denoted by I, imaginary unit. So now we have this imaginary unit. So this is additional element, not real number. So this is the main idea. Very long time, people considered complex numbers as some artificial numbers, non-real, non-useful. But nowadays, they used very much in electrical engineering, and in particular in wireless communication. In wireless communication, complex numbers are the main, all signals are presented by complex numbers. So complex number is such number, x plus I, y, where x and y are real numbers. We can introduce real part of this number, x, and imaginary part of this number, y. And since you, okay, question from Jesper. Jesper, yeah. Just a moment. Yes, per. Good question, good question. How we define square root of I? It will come. It will come a bit later. It will come a bit later, and we would be able to define square root of any complex number, Okay, so when you see already these two coordinates, you have the image of plane and Cartesian coordinates and x and y. So this, of course, you want maybe to, no, it's very natural. It's very natural to represent this number z by vector on the complex plane. No, no, it's not complex, but on the usual plane, two-dimensional plane. And this book is very good. There's some historical references, and was Guy Argand. I never heard about, so Gauss. No, okay, it is very natural. So you take this pair of coordinates, and you can define the length of this vector, the square root of x squared plus y squared, and you can define angle theta between real axis and this vector. So this is geometric representation of complex numbers. Each complex number can be represented by vector. Where it is used, no, in physics, no, maybe used, but not so much, maybe. Okay. Now we start operations on complex numbers. Those who had some course in algebra, they maybe have the notion of field, number field. So, for example, real numbers, this is number field. Rational numbers is also number field. What is number field? They define it operations of multiplication, division, addition, subtraction. These operations are commutative and associative. So, in fact, complex numbers, it is a field, also a field. More or less, this is the third example of the field which you meet in your life. Maybe you also, if you had course in algebra, you consider it also a field of residual classes. If you have never heard about algebra and groups and field, then just forget this. So we start operations. This is complex numbers is very special field. Here we have operation of conjugation. For each complex number z, conjugate number here is just minus. One can say why this operation formally look, no, we wrote here minus. What is the meaning behind this? If we apply this operation second time, we will get the same number z. We will get the same number z. So this operation has the following property: its square is equal to the unit operator. So these are such operations. We can consider them in other algebraic structures, which has the following property: square equal to identity. And this is operation of conjugation. On real numbers, the only conjugation is identity. On rational, also the only conjugation is identity. So more or less, complex numbers is the first case where conjugation is this operator which have the square is identity is non-trivial. But in the course, we would not use this property, just remember this and go further. No, real part of conjugation is the same as real part of x, of z. Imaginary part of conjugation is minus imaginary part of z. So how it look on the plane? If this is number, then conjugation is just we change the sign of y. So this is vector z, and this is z star. One note about notations. Typically, in practically all books, people use not z star, but they use z bar. No, z star maybe in algebra people use, but in physics and electrical engineering, z and over z is line. So this is conjugation. Now I think this book in some places not so well written, I think, from pedagogical viewpoint, because they start with example 1, 2, and they consider very complex function, logarithm of complex number. It is a special story, and we will be back to this, and now we just ignore this example. Then the second example, I think, is not better. The second example is not better. This is Z1 plus I in the degree I. It's also very complex notion. We shall come back better later. Modulus. The modulus of complex number is length. It's length of this vector on the plane. So we can write in this way. Argument. This is this angle theta. So we're starting from real line and go up. Typically, argument is defined between minus p and p, or then we have negative arguments, or between 0 and 2 pi. So it depends how you like to do this. No addition, operations. This is operations of the field. This is operations in algebra of the structure called field. Addition is very simple. Sum on subtraction, the sum of real parts plus I, the sum of imaginary parts. So on the plane, I think maybe you had the course of linear algebra, and you know how to construct the sum of two vectors. For example, this one vector, this is another vector, and the sum would be just vector connecting these points. In the same way, we can define subtraction, and but typically we never use this because we use algebra. No, geometry is maybe good for intuition, but okay, it's just good illustrations. It's good illustrations, but we never use this. Okay, yeah, that's multiplication. Multiplication is given as it should be. If you multiply, just open the brackets, and use it I product I square is equal minus 1. So this is generated by products of two i's, the product of two i's. No, this you don't need remember because you can just calculate. It's very simple. Division is a bit more interesting. You have two numbers right in this way. What we do, we want to that in denominator would be a real number. So how to produce real number? We multiply to the complex conjugate, and then we get the square of absolute value of model, the square of modulus of absolute value. So maybe you did this somewhere. No, this you need not to remember because it's coming from this. Only you remember if you have such number, multiply denominator by x2 minus y minus I y2. So the complex conjugate. Yeah, so this is division. This is division operation. We go quite quickly, but you can read in the book, and then you will get many exercises, but okay. Now coming more interesting. So this is Cartesian representation, if you have seen Cartesian representation. There's a question, is field expansion possible on complex numbers? What is field expansion? Field expansion, you mean as in real numbers which we can expand in extension. It's very good question, and we're going far beyond. The question is the following. For example, we were in real numbers, and we wanted to solve equation x squared equal minus 1. After 100 or 200 years, people understood that it is impossible. that it is impossible. They thought, let us add two complex numbers, two real numbers, just one symbol, one idealistic number, I, such that I squared per definition is -1. So we can solve equation x squared equal minus 1. But then, for example, one can tell, can we solve equation x in the degree 5 equal minus, or x in the degree 8 equal -1? Can we solve any polynomial equation? We know that, for example, quadratic polynomial or cubic polynomial in real numbers not always have solution. It happens, and it is very specific of complex numbers, that any polynomial equation has n roots. So there is no need for more extension. So the field is possible to prove, and it's called, in fact, this is a part of course in algebra, and it's called the main theorem of algebra. That if you take any polynomial, right, equal to 0, then you always can find all its roots in the field of complex numbers. So this in principle, theoretically, it could happen that some polynomial, even with real coefficients, maybe without roots in complex numbers. Then we should add to complex numbers, so-called additional roots, and we get bigger field, and so on and so on. But the main theorem of algebra tells us, if you add to real numbers just one letter I, then you can solve in this field of complex numbers any polynomial equation, find all n roots. It is not for all fields. For example, in algebra, those who will go to algebra, you will find so-called fields of p-adic numbers. Fields of p-adic numbers. They are constructed starting with residual classes. These fields have precisely this question, maybe that was interesting for Jesper. In this field, we can solve, for example, equation x squared equal -1, add one element, and get some quadratic extension. So where this equation has solution. But, for example, there exists polynomial which has no solution. We add the roots of this polynomial. And so on and so on. In periodic case, we construct a tower of many extensions of the fields. So we add more and more roots. Finally, we should make union of all these extensions, and we get terribly big field, the complex periodic numbers. But it's a subject of algebra, and only if you go very deeply in algebra, you meet this. Okay, now we're back. We're on Cartesian plane. This is complex number. It is its coordinates. You remember from school that you can introduce polar coordinates, да? Polar coordinates, this is just by Pythagorean theorem, this is x given in this way and y given in this way. So if you put in the formula, for complex number, then we get that it is that z is equal this radius and this sum cosinus and sinus. Of course, it is 1. So if you multiply z by z conjugate, we get square of this radius. This we have already used. So then these numbers of this form, they are on the unit circle. Because square of this plus square of this equal to 1. So it's good to remember. This property is very useful. That if you have cosinus plus I sinus, you are on the unit circle. Then they want the author of this book, by using ordinary differential equation, want to motivate this formula. That cosinus theta plus I sinus theta can be denoted as exponent I theta, and then you can work with this exponent as with any exponent. As you work with exponent e in the degree x, you can work with this exponent in the same way. No, I don't like this derivation because in any event, it's already complex equations and so on. And he told us this solution of this equation is this number, but it is better do as it was done. It was done. So this is Euler formula. This is Euler formula. Was great German mathematician, but surprisingly, half of his life he worked in Russia, in St. Petersburg. He was invited by Ekaterina the Great, and he was paid by gold for his theorems. I think maybe only one case in the history of science when mathematician was paid by gold for proofs of theorems. So for him, it was just definition. He thought, let us consider this sum and denote this by this symbol. Then we can show that we can operate with this symbol in the same way as in this usual exponent. So my suggestion, just memorize this Euler formula and then work with such exponent as it is usual exponent. Then how we can justify it. Later we shall show that this function can be expanded in the Taylor series, and this Taylor series has all properties of exponent. Now, if we denote this by by Euler formula in exponential form, then any complex number can be represented in this form. So this is polar representation of complex numbers. This should be memorized. So this is very good formula and it is useful everywhere. So any complex number, I just repeat, complex number can be represented as its absolute value or the length of a vector on the complex plane, exponent I theta, where theta is argument of this complex number. And then when you, for example, multiply complex numbers, add, and so on, you work with this as with usual exponent. If we make conjugate to get conjugate to this exponent, we should remember always that it has this form. So it would be minus here, da? So minus coming here. So conjugate to that in polar form is the same radius. Radius is the same, but argument is different. The argument is different. Yeah. So this formula, yes, yeah, these formulas we memorized. Again, examples are not so great. Again, with this logarithm, we shall maybe next lecture solve many problems and which are not so advanced because it's again not the simplest complex number to start to work with the polar formula. Moivre's theorem, no, it's very often complex analysis is applied to prove something in real analysis. Maybe we will back to this theorem, maybe not. So this is application of complex analysis to prove something for real analysis. So we do something in complex plane, then take a real part from both sides, and we get some equality in real numbers. So this is, or imaginary parts, we get some equality in real numbers. So this is, you can go through, it is in very detail. Exponential representation of trigonometric functions. Now look, if you have this formula, Euler formula, then we make conjugate, just make conjugate on this side, there is minus. So we get this. Now let us add these two equalities. And we get that cosinus is represented in this way. So this is complex Euler formula for cosinus. In the same way, sinus. There is I in denominator. They should be memorized. We use them a lot in complex analysis. That cosinus is the sum of two exponents, exponent and conjugated exponent divided by 2. Sinus is also difference of these two exponents divided by 2i. We can also represent tangents. Formula for tangents is not so nice. We can go further and consider hyperbolic functions. For example, we can write cosinus iw, put here this imaginary theta, and get this formula. So this hyperbolic cosinus. And we get this formula we knew from usual course of analysis. Yeah, such hyperbolic cosinus is equal the sum of these two exponents divided by 2. But now what is interesting that it is usual cosinus, but imaginary I multiplied by argument. So these two things which were considered in usual analysis as totally different, hyperbolic function and usual trigonometric function, are in fact very similar. They related to this equality. Maybe therefore we denote hyperbolic cosinus as cosinus, because it's cosinus, yeah? In the same way we represent, we have equality for hyperbolic sinus, here is I. For also for hyperbolic tangents, So this is connection between trigonometric and hyperbolic functions, which is in the framework of complex analysis. Now we're coming to really important section. No, this representation of trigonometric via hyperbolic via trigonometric, it's interesting, but not so much useful. What is useful everywhere in applications and mathematics? This is possibility to get all possible complex roots of unity by using Euler formula. So we start with this formula. So take exponent in 2 pi k. What does it mean? If k is equal to 0, it is just vector on the x-axis. If we started to rotate it, we shall get 2 pi. We shall again come to the same vector. So this vector is always 1. It's always 1. So we have the coordinates. This vector 1 on the real line. And if you make rotation to pi, we come to the same vector. So no, maybe it's good even to remember somewhere that exponent 2 pi k, 2 pi I k is equal to 1. And minus its rotation in different sides. So this is the same vector. And now we rotate it 2 pi, again here, 2 pi, again here. And we can rotate as many times as we want. Any k, we get the same vector. So this exponent is always equal to 1. Now we can find all possible roots of 1 in of degree n. So we write this formula. Square, no, not square, but the root of degree n from 1. We do the following. Instead of 1, this 1, we put this right in this way. And then, as I told, with Euler exponent, you can work as with usual exponent. So it would be this formula. Now we apply Euler formula. So it is cosinus of this argument plus minus I sinus of this argument, minus coming from minus, because sinus of minus is minus. And now we can find, this is formula for all possible roots of unity, and there are many. We shall see how many now. Of course, we suspect that there are just n roots. And let us go and step by step, yeah? So, for example, k equal 1. If k equals 0, so this is cosinus, it's 1, it's 0, so it is just 1. So always among roots of unity is 1. Now k is equal 1, root of degree 1 over n. So this is this number. Root of the degree k 2, this is this number. Please remember this machinery, yes, because in your pre-exam and in exam would be such problems. It's the most standard, this is the basic, what should do the student after this course. Be able to find root of any degree from at least plus minus 1, but in principle from any complex number. So, and if we take the root of degree 1 over n, we again n disappear. So this is exponent 2 pi, it is again 1. So what we have seen, we start k equals 0, get different roots given by this formula. And when we, how many it was? K0, n minus 1, and we got n roots. And then the root this number n plus 1, when there is n, it is again equal 1. We see that the roots of unity in complex numbers, if you again know algebra, it's example of so-called cyclic group. Cyclic group. When we have some element, and its degrees give us the whole group with n elements. So yeah, n plus 1, we get again this number, the root for k. So this is cyclicity of these roots. Cycle group. If you get minus, the sign minus, it is again the same. So this formula, you can forget about plus minus, write just this, because if you go to negative k, it is the same as to go to positive n minus k. You can remember this formula, or can just not really, you need not maybe even remember this, but remember only this formula. And then you take roots by using this formula as it should be. And here is Euler formula. Okay, so we found all roots from 1. Yeah, what is the absolute value of this root? It's of course 1. So all the roots, it's very important. And your intuition should be with this, that all roots from 1, they are on the unit circle. So the n points on the unit circle. One of them is just over real line. So all roots from 1 are on the real circle, on the unit circle. This example, this is good example. This is not logarithm, this is very good example. We can find square roots of 1. Of course, one of them is 1. And the second is given, we put k equal 1 in the previous formula. So we get exponent in the degree ip, it is minus 1. So square roots of 1 are the same as were in real numbers. For square roots for 1, we did not get anything. We suspect that it should be for all roots from 1, да? Because how we got complex numbers? Complex numbers we got starting with square roots of minus 1. And we suspect that problems are with roots from minus 1. But we shall see now that the problems are already with roots of 1. And that the number of roots from 1 is, of course, it's much more. So these are square roots. They're on the real line. But if you take cubic roots, so this is this formula divided by 3. If the roots of, for example, degree 7, the only difference would be that in denominator would be 7. And we can calculate these numbers. So, for example, if k is equal, of course, 1 is always 1. If k is equal 1, you know maybe from school what is cosinus of 2 pi divided by 3. What is this? 2 pi, this is, okay, so you find these numbers. It's not precisely 60 degrees, but you are in this second half plane. Да? So this is this number, and this is this number. You can just calculate this cosinus and sinus. But what is important, and you should account, that these roots are conjugate. They are conjugate. And this is always, if you have root of some, for example, of degree, if you have the root, for example, of degree 5, of course, 1 will be always the root. And then it would be 2 pairs, 2 conjugate pairs to get 4 additional roots. So if you have 7, it would be also, so the roots are always this and this. If they are not on the real line, they are of this type. On the real line, we can have only, if the roots from 1 can be only plus 1. Okay. 1/3. Yeah, so there are these calculations. Now it's more interesting, the roots of minus 1. Now, formula, what is the formula? What is minus 1? So here it is, here we should just remember how it's look. Minus 1 is on the negative part, of this coordinate system, and minus 1 is here. So the angle is pi. We go this half circle. So the main formula, unfortunately, it is not written here. Let us write this formula. Let us write this formula that that -1 is equal exponent, and here is pi. It is pi, I pi, yeah. So if you take exponent, maybe we write this in LaTeX, here slash, that it is pi, that it is number pi, Okay, so this we remember that -1 is it's good to remember some formulas. So -1 is exponent I pi. Now, for example, what is I? Да? Let us also represent I, imaginary unit. It is equal. Where is imaginary unit? We have this coordinate plane, and imaginary unit is here, up. So the angle is pi divided by 2. So it is exponent I, and here is pi divided by 2. So this is I. Now, you can write also minus pi. Minus pi here would be 3/2. Here will be 3/2. So it is good to have some image of this, and know what is -1 in the exponential form, +1 I minus I. So we write -1 in this way. So this is I pi. But what is the most important? That we can add any this 2 pi k, this 2 pi I k. This you should remember that always when we write this exponential form, we can make any number of rotations additional, and we again come to the same point. So if I take -1, it is here, and then I start to rotate, 1 rotation and so on, as many rotations as I like. So you should always take into account that -1 is not only I pi, but also this. Then we write this, and then we write this formula. And then we can find all possible roots of degree n. K is going from 0 to n minus n. So maybe we write this also. That k equal 0 up to k equal 0 up to n minus 1. And you can write all roots of -1. No? And then it's also good example. They consider, for example, square roots of -1 by this formula. So this is this. And then we get I and minus I, as it is expected. Now cubic roots of -1. Again, this general formula, and here is 3. What is the difference between roots of 1 and -1? In 1, here is even number, 2k. In -1, here is +1. And then we again calculate these cosinuses, and we get these numbers, and we again see that they are conjugate. In fact, it would be for, it is algebraic, in fact, fact that if you take any polynomial of even degree, of odd degree, it is always would be one root on real line, and other roots would be in pairs, root conjugated. So this is just simple example of this very general statement. This book contains some appendixes for engineering. but I'm not expert in electrical engineering. I suspect those students who will study electrical engineering, they will study these electrical circuits, and we go further. We go now to functions. We go to functions. So it was first part, the short introduction to complex numbers. And now we go to complex functions. So what we should remember? We should remember such words: Cauchy Riemann conditions. So everybody who passed this course should know very well these Cauchy Riemann conditions. Either you should memorize them, or as we shall do now, derive them. Derivation is very simple. So first, we define derivative of function of complex variables. In fact, here we can divide by complex number, and we can divide, this is just usual derivative. Yeah, we go here. So this is a derivative of complex function. So in fact, in any number field, we can try to define derivative, but we should have also the notion of limit. What does not mean that complex number go to zero? It means that its absolute value or modulus go to zero. So this radius goes to zero. Now, this is definition of complex derivative. This is definition of complex derivatives. Now, complex number can be represented as two real numbers, and when complex number its length goes to zero, of course, both coordinates are also go to zero. So on the plane, if we have some radius and its radius is go to zero, its coordinates also go to zero. So in fact, this is this limit. This is this limit. And here is the point that you consider it maybe in your course of multivariant analysis, that if you have few variables, this limit may depend on the order. Limit may be not. So, for example, we can write in this way, first with respect to y, and then with respect to x, or in this way, So if we do, for example, in this way, so we set just zero, this we set just zero, and go just with this. We get partial usual derivative with respect to x. Now let us be, so this is, we go through real line. When you started multivariate analysis, maybe you studied that when you studied partial derivatives, you consider it that we go from this direction, and typically we consider from above, over vertical line and over horizontal line. We do the same. So if we go this way, we get this, and if we go in this way, we get this. So if this limit in complex plane exists, these two numbers should be equal. This is this Cauchy Riemann equality. It's coming from definition of derivative of complex valued function. That this derivative did not depend on whether we go through this axis or go through this axis. So this is Cauchy Riemann derivative. One of the main part of development of complex analysis was to prove inverse. That if we have this Cauchy Riemann condition, then we will come to complex numbers. Then we will come to complex analysis. But for the moment, we just go. Now, if you have function of with complex value, so this fz is again complex number, it can be written in this form. This is real part of this function, and this is imaginary part of this function. So then we put, instead of this f, its sum. And here we also, in this equality, we put instead of f, this sum. And then we collect O without I and O with I. So we get two equations. So these are Cauchy Riemann conditions in real form. There is no more I. Look, in the previous Cauchy Riemann conditions, we had this. So because this was complex number, and here is I. Now we want to eliminate complex numbers. So we write F in this way. So, and then we get to Cauchy Riemann conditions. So, I think in the exam would be one of the questions, typically, I don't guarantee, we shall see, derivation of Cauchy Riemann conditions. And you do this very simply, yeah? So, so you write this derivative, and then first go through vertical line to 0 and get one derivative, and then go through horizontal line to 0 and get another derivative. And they should be equal, So, and then if you need, you can write F in this way, and you will get this Cauchy Riemann conditions in this way. So these are two equations, system of two equations. Now, this is not typical. Typically, people never use in mathematics Cauchy Riemann conditions in the polar coordinates. But in physics, in electrical engineering, they do. So now we shall write Cauchy Riemann conditions in polar coordinates. In fact, Riemann is this famous Riemann whose hypothesis on Riemann zeta function is still unsolved. And there's $1 million to get to solve this hypothesis, to prove this hypothesis. So it is the way to earn $1 million. Okay, so what people do in engineering? They go to polar coordinates. This is radius. This is formula for theta. And then they want to write Cauchy Riemann conditions. They should find partial derivatives and put the expressions in polar coordinates. So, for example, let us consider this derivative. F, and now here was Z before, but now there this R and theta, where R is given by this formula and theta can be found from this. First of all, we use this formula, how we calculate the derivative of composition of functions. So F, and into F we put R as function of X and Y, and theta, which is also function of X and Y. And then we started to calculate first dF dr with respect to radius, and then derivative of radius with respect to X, derivative of F with respect to the second function, theta, derivative of theta with respect to X. For example, they claim that derivative of radius with respect to X is equal cosinus theta. How they prove this? So we have this equality that radius square is equal X square plus Y square. So now we take derivative with respect to X. This disappear. Here we have on this side we have 2X, and here we have 2R and derivative of radius with respect to X. Now we can find derivative of radius with respect to X. It is cosinus theta. In the same way, we can find derivative of theta with respect to X from this formula. So, and we get this, So now this is still preparation to Cauchy Riemann conditions in polar coordinates. Now, in the same way we find this, it would be not on exam because it's just plain calculations, but to have picture, okay, there is derivative of composition of two functions, yeah? So finally, we get this Cauchy Riemann condition in polar coordinates. Now, if we represent F as the sum U plus IV, we get these two equations, system of two equations. Now, we're coming to the main notion, to the notion of analytic function, to the notion of analytic function. Suppose we have function of complex variable with complex values, and it satisfies Cauchy Riemann conditions in all points. So derivative, this is equivalent that complex derivative exists. That complex derivative exists. So we can calculate complex derivative in this way if we want to have connection with real analysis. But in principle, we can calculate it directly as the limit. So this limit exists precisely when Cauchy Riemann condition is satisfied. Or in this way, or in this way. No, in some ways, just to repeat, it is polar coordinate representation, has nothing special to do with analyticity. The author just wrote it to recall you that it exists, that this representation exists. We are interested in this. We are interested in this. Yeah. So this is polar representation. We don't, okay, forget about this. Now, suppose that we have some function which is infinitely differentiable with respect to z in any point of some domain z. So one derivative exists, second derivative exists, and so on. Either we can define these derivatives directly at limit, the increasing of function divided by delta z, or we can say that Cauchy Riemann condition is satisfied for f. It is satisfied for its first derivative, is satisfied for its second derivative, and so on. Such function is called analytic. Such function is called analytic. It is maybe not the best way, because when you use analytical function, you use that they can be represented as power series with respect to z, but it is more or less historical way. In this way, people came to analytical functions, to analytic functions. But we follow historical way, and we gave, so on the exam, when, if it would be theoretical question, please give definition of analytic function. So this is definition, that it is infinitely differentiable with respect to z, or all its derivatives is differentiable, infinitely differentiable in the sense of real analysis, and all derivatives satisfied by Cauchy Riemann condition. Testing analyticity. This also can be a problem, at least at this pre-examination. So how to get knowledge some function is analytic? So that you should check Cauchy Riemann condition for this function, and see that it can be checked for all derivatives. No, they do this. They calculate the f dx. They consider this function, and then they calculate this and they see that they coincide. So function is analytic. So to check that function is analytic, you should check Cauchy Riemann conditions and see that they would be they still would be satisfied for all derivatives. The same they can do for z in the degree n. For z, no, they prefer to do this in polar coordinates, but it's more or less for training. Finally, they came to this formula. What is the main lesson from these two examples? Of course, we can check Cauchy Riemann conditions, but sometimes, and practically always, it is easy to check that just usual derivative in the sense of complex variable exist. And you see that this z, it does not differ so much from x in real analysis. So all derivatives would be calculated in the same way with respect to z. If function is depend only on z, if there is no, it can be function which can be represented as just function of z. If you take function x multiplied by y, then this function we cannot write as function of z. So then it would not work. But if function fz is really written as z variable, then you can differentiate as you did in real analysis. So the main message, If function is written in this form, polynomial of z, exponent of z, cosinus of z, any good function of z, then you can differentiate as you did. Now, finally, about this notion of, it should be also memorized, it's basic definitions, analytic functions, Euler formula, and entire function. What is entire function? This is the function which is analytic on the whole plane. For example, any polynomial is analytic over the whole plane because derivative exists in any point and infinitely many derivatives. Exponent is analytic on the whole plane. Cosinus, sinus, all these functions are entire. In some book, people taught entire analytic function. No, here to be short, he just taught entire function. Yeah, he also wrote this message. Derivative of each of these functions is the result, yeah, by treating z as a single variable, even with sum of two independent variables. So do this without any doubts. Now, the demonstration that fractional root of is not analytic. No, they use Cauchy Riemann condition, but I propose just differentiate this function as usual function of z, and then you will get z in the denominator, square root of z in denominator, and in the point 0, it is singularity, it goes to infinity. So in the point 0, this function is not differentiable as function of z, and so it is not analytic in the point z equal to 0, so it is, of course, not entire analytic. No, I would not, I'm not so fan of condition of Cauchy Riemann. I know that it is very useful in hydrodynamics. No, I'm not sure that so many of you would work in hydrodynamics, but even in electrical engineering, people just consider typically signal as a function of complex z, so, okay, now Laplace equation. This is important for those who work in applications. So, we have function f. Let us it will be analytic in some region containing z. We consider its real part and imaginary part. We write this equation. This is Cauchy Riemann condition, and this is Cauchy Riemann condition. And then we differentiate the second time. So it would be the second derivative of x. Here would be the second derivative of v, and here would be derivative of v dy dx. And here, how they do this, just a moment. We should get this sum. This is so-called Laplace operator. Second derivative of x. And and here would be derivative of v, which is here would be in the direction dx dy, and here would be dy dx. Here we shall use this theorem from your course of multi-variable analysis that mixed derivatives, they do not depend on order. If function is two-time differentiable and second derivative is continuous, then derivative dx dy is the same as derivative dy dx. So we use this, that these two would equal, and here we get such equation. Second derivative of u plus second derivative of u with respect to y, it's equal to 0. And second derivative of v plus second derivative of v is equal to 0. This equation, this sum of second derivatives equal to 0, is called Laplace equation. And this operator, this differential operator, so the notion of differential operator, so partial d square dx square, d square dy square, is called Laplace operator. In physics, they like operator nabla. Unfortunately, the author did not write this operator. So this operator is just vector of partial derivatives. So n square of this nabla operator is you work with partial derivatives as just with coordinates. It's sum of second derivatives. So, typically in physical books, this operator is denoted by delta. So delta without square, but inverse delta. Usual Latin large letter delta. So delta square, delta u equals 0, or nabla square u equals 0, or nabla square v equals 0. These are Laplace equations. And we prove very important thing, which is used in many applications, that if we take analytical function, and if we take its real part and imaginary part, and if we take second derivatives, the sum of second derivatives is 0. Laplace equation is equation of electrostatics. All electricity is based on Laplace equation. Even acoustic waves based on Laplace equation, and so on. So one way to find solution of Laplace equation is to find analytic function, then take its real part and imaginary part, and then you automatically get that they would satisfy the Laplace equation. So this is useful. So remember this thing. If you have analytic function and take its imaginary part and real part, both these real functions satisfy to Laplace equation. No, derivation is very simple. It was on the previous page, yeah. And this is just about mixed derivatives. Such mixed partial derivatives are equal. Okay, good. Determination of an analytic function. This is this would be just complementary, because I never seen such people use this. It is, of course, this is interesting, it is correct, but I work in many applications. I never seen that it was useful, but it's not bad to know. Maybe you will be in some application where you can use this. For example, if you have analytic function and we have its real part and imaginary part, and suppose we know only real part, then we can reconstruct its imaginary part. So this is, it means that, and we know this already from Cauchy Riemann conditions, that real and imaginary part of analytic functions is not independent. They are connected by Cauchy Riemann condition. So therefore, we can use these conditions to determine, for example, imaginary part if we know real part. And here's this scheme. It is more or less for your curiosity. It would not be in theoretical questions, but in any event, it's very clear. We write Cauchy Riemann condition, one of these equations, in real form. This is this equation, just Cauchy Riemann. And then we want to find V. So what we do? We integrate this part with respect to this Y. So because we know derivatives with respect to the second variable. So we get this integral, but X, this is important point, X here is parameter. So this constant, so when we integrate, we don't pay attention to X. We just integrate this as function of Y. X is frozen. But what is the most interesting is that this A is not just constant, as enforced in your usual analysis. It's function of X, because X is parameter. And since this depends on parameter, this A is also dependent on parameter. Then there is how to find A. So its derivative is depend only on X. It does not depend on Y, because it's constant of integration with respect to Y. So we get this equation, and from this equation we find this constant A, which is constant with respect to second variable, but it is not constant with respect to the first variable. So this is function of X, and here is already usual constant, because we integrated with respect to all variable. So to find imaginary part, if you know the real part, we should integrate this function. So this is formula to get imaginary part of analytic function if we know real part. In this way, it's never work, but how it works sometimes? You have just function u, any function u. We don't know about not any analyticity and so on of two variables, and we want to construct analytic function such that u is its real part. Then we do it this way. So we integrate, find v, and then if you go back, these functions are connected by Cauchy Riemann condition. So the function u plus I v would be analytic. So from any function, it also should be somewhere in your brain. Also, this is not, details of integrations are not so important, but it's important, to remember, that it is always possible by having just one function of two variables to construct analytic function by this formula to find its imaginary part. And then they consider example. And this is just we put in this formula these concrete functions. We calculate derivative with respect to y. This is this one. Then we calculate this derivative with respect to x and integrate with respect to y. So, and then we integrate, and we get somewhere this function. So it works, but I'm not sure that it has so many applications. Okay, now we're coming to really important part. Because before what we just studied about functions up to now, that for function of complex variable, we can define derivative as in usual case, because we can divide by delta z. If we want to see condition when this derivative exists, then it is Cauchy Riemann condition. Then we introduce analytic function. So function which is infinitely differentiable with respect to z, or that all its derivatives satisfy Cauchy Riemann condition. And now we're coming to integration. I just put more light. It's a bit too dark, at least for me. Too dark. And now we're going to integration. We want to define, we have 2 points, Z1 and Z2 on the plane. Here, I was wrong at the beginning. No, geometric picture is not so important when we add complex numbers, multiply, not important for algebra. It's just illustration for algebra. But geometric picture is very important when we start integration with respect to curves, to contours. Typically, contour is closed curve. But okay, in this book, pass. I would maybe use better word pass and reserve contour for closed path. But okay. So we want to consider integral between 2 points with respect to some path connecting these 2 points. For example, this is one point, Z1, this is point Z2, and there is some path, some trajectory going from, for example, Z1 to Z2. This is another path and so on. So each 2 points we can connect by many trajectories. What is important? They should not have intersections. For this trajectory, this small trajectory is not good. So if we consider its ends and they are connected by this curve which have self-intersection, we don't consider such. So we consider only trajectories which have no self-intersection. So this is still good. It is it's very not so good, not so straight. Okay, so this is still good. Now, how we define integral with respect to trajectory? So what is fz dz? Where z is trajectory. It is the following definition. We represent this z. As can we go here? Not. We can go here. Good. We represent this z as some curve, so as some function of parameter t. So zt, and t is between t1 and t2, less or equal. This is coordinate x depending on t, coordinate y depending on t. How we find dz, this dz? As usual, dz is z prime dt and x prime t plus I y prime t dt. So now integral, this is, I just cannot write symbol of integral. This is integral with respect to this q of fz dz is integral from, now we're going just to usual one-dimensional Riemann integral from t1, it is LaTeX notations, to t2. We put zt, our curve, in z, and instead of dz, we write z prime dt, z prime dt. So this integral, if you should first parameterize, the trajectory should be parameterized. You should put some parameterization. And then you can define integral from z1 to z2. Yeah. Yeah, I agree that there are infinite number of possible paths, and they should not have self-intersection. Otherwise, theory does not work. They can be taken between these endpoints. Two such contours are shown on fig 3.1. No, this is one path, and this is another path. If you want to make closed path, to make a contour, we should select direction. We should select direction of motion. So this is clockwise. So this, and then we want to close it. We should go clockwise. So this is contour when direction is the same. So if you go here such way, and then we want to go here such way, it's not good. It's not good. So you should select direction. Of course, you can select direction counterclockwise. Yeah? So in this way, but then you also should go in this way. So when you see this integral over the closed curve, you always should know is it clockwise or counterclockwise. Typically, we select counterclockwise direction, not clockwise. Typically, even in some books, people even here write the direction. So, for example, this integral is not just here circle, but circle with such arrows. So, if you integrate over this circle, here would be circle with these arrows. If you integrate circle in another direction, here would be circle with another arrow. So we go back here. Infinite number of possible paths. Yeah. In general, it's of course correct. We can expect such integral depends on which path we take. So, for example, we go this trajectory from this point to this, or this trajectory. As we see, each trajectory has its own parameterization, this zt function, and this dz is different. This dz is different. So the main point is here. The main point is here. Dz is different. So in principle, integrate with respect to this or with respect to this, we can get different answers. But what we are interested, and it would be a property of analytic function, we are interested, it would be a rather long way to this, but we just start. We are interested in such functions, and we shall see that these are precisely analytic functions, that integral does not depend on the trajectory. So integral from this point to this over this is the same as integral over any other trajectory which goes from this point to this. So we are interested in this condition. So we are interested in such functions that we have this condition. The integral does not depend. But we want to have, as I already told, we want to have contour. We want to have the same direction. So I told the integral from this point to this is the same as integral from this point to this. But here, this direction is here, for example, and this direction is here. It's not good. We should have direction this one, and then go back this one. When we go back, parameter t changes its sign. So the condition that we go from Z1 to Z2 is the same as, again, from Z1 to Z2, can be written in this form. Condition that we go from Z1 to Z2, and then it is, notice, no, they wrote, it is, what is written here? I think it should be, it's not good. We go from Z1 to Z2, and here we should write right direction from Z2 to Z1, to Z2 from Z1. Then it is 0, the sum is 0. So integral over contour, we go from Z1 to Z2, plus integral from Z2 to Z1, the sum is equal to 0. I would like to write here, that it's sum of integral, no, I would not write, but just remember that one integral is going from this point to this, but the second should go from this point to this. Then the sum is 0. The sum is 0. So we are interested in such functions that integrals over closed contours are equal to 0. And I hope that, yeah, we have time. I hope now we should recall one. I even check with your teachers, and you should have in the course of multivariate analysis of many variables, so-called green formula. Green formula is very useful in engineering, not only in electric, but even in construction and so on. What is the meaning of green formula? It is precisely, we have contour, we also have closed, for example, in green formula, we have, for example, such curve, we have some integral over this curve, over this trajectory, closed trajectory over contour, and then green formula can represent this integral as integral over domain inside this curve. So one-dimensional integral is connected with two-dimensional integral. In 19th century, it was greatest discovery in mathematics. That it's very strange, yes? That this integral, one-dimensional, we know function only on the boundary, But this integral is two-dimensional. Here we should know function inside, and they are connected by green formula. I don't remember who was Green by the name. I think he was English. Yeah. What is green formula? No, I hope it was proven because it was, no, Joachim Toft wrote me that you should know it. Consider two functions. We forget about complex analysis at all. We go back to analysis of functions of few variables. We have two functions, g depending on two variables and h depending on two variables. And we want that they are differentiable, derivative exists and they are continuous, that we can integrate, that Riemann integrals are defined. Then we consider integral over contour, over a closed curve. And here we can have any parameterization. What is also interesting, we can any parameterization on this C. We can introduce one variable t, integrate another. It is the same. Then this integral is equal, I don't know, maybe in your course you even had such notion as differential form. This expression g dx plus h dy is the simplest differential form of two variables. It's a step to tensor calculus. No, I suspect that your course, no, maybe in the course of differential geometry or somewhere you have differential forms. So the integral of this differential form with respect to closed contour is equal to this integral over domain inside this contour of difference of these two partial derivatives, No, the proof exists in this book. You can go to appendix, but we shall not prove. Now, what we do? We take our analytic function. We want to apply this formula from usual analysis of few variables to complex analysis, yeah? Here was no restriction to G and H. Now we write our integral, which was before, over the closed curve. Now we know what is Fz, so it is can be represented U dz can be represented in this way, U dx v dy, and plus imaginary part, and suppose now we don't know that this function is analytic. Suppose that this, we know only, we have some, there will be two parts. We want to connect two notions. One notion, that function is analytic, so it is satisfy Cauchy Riemann condition. And the second notion is that integral over a closed curve is equal to 0. So, for example, this formula gives us this connection. For example, suppose that our function, we don't know at the moment that it is analytic, that derivative exists, Cauchy Riemann condition is satisfied. Suppose that this function has this property, that this integral is 0, So this, now we select as G this U, as H minus V, so we want to identify this and this. We identify this. If complex number is equal to 0, both real part and imaginary is equal to 0. So for us, it's enough that this is 0. So, and now we know that suppose that integral of some function over any closed curve is 0. Then we have that this is equal to this, and we get this. And surprisingly, but it's not maybe so surprisingly,